Hi everyone, this is Raj and this is the second video of the video lecture series of Semiconductor Physics. So in the first video I have actually explained the electronic densities of different type of materials and the significance of the electron density of semiconductor. So in this video I will be continuing my discussion with motion of electrons. So I can classify this whole discussion into two subcases. One is motion of electron without any external electric field and motion of electrons with an external electric field. So at first I will start with case 1 without any external electric field. So at first I mean before starting our discussion I would like to remind you something from our 10+2 level, that in our 10+2 level we studied the kinetic theory of gas. There we studied this formula E equal to kT, where E was the kinetic energy of particles, K is the Boltzmann constant, and T is the temperature in Kelvin scale. And we know that at T equal to 0 Kelvin, which is actually known as absolute zero temperature, the kinetic energy of particles becomes 0. That means the velocity of the particles becomes 0, which means the particles are in stationary state. So this is the thing which we should remember before studying this motion of the electrons within the within materials. So now I will start our discussion. Let's suppose we are dealing with a material at T equal to 300 Kelvin, which is actually known as room temperature. So the electrons which are inside this material, they are not having a kinetic energy equal to 0. The kinetic energy of these electrons is not equal to 0. So the velocity is not equal to 0. That means the electrons are not in stationary state. That means they are moving. So how the electrons are moving? So if we consider this is an electron without any external electric field at T not equal to 0 Kelvin temperature, this electron has the equal probability of moving in any direction, or we can say it has a equiprobability of moving at any direction. That means this electron moves in random directions, and finally it comes to its primary state, and then it again starts its random motion. So this kind of random motion is known as Brownian motion. So up to this I think this is clear. But here comes a question, that if all the electrons within this material are moving all the time and in all the directions, then why this material is not producing any current? Because we know that if we don't apply any external electric field, then material don't produce any current. But why? Electrons are moving, then why not it is producing any current? Because we know that uh, if electron is moving from one place to another place, then it produces a current, and the direction of the current is the opposite direction of the flow of the electron. So why not it is producing any current here? So here is the explanation, that if we consider there are n number of electrons in this material, and at a particular moment u1 is the thermal velocity. Why it is called thermal velocity? Because if we put this material at T equal to 0 Kelvin, then there all the electrons are in stationary state, then there is no velocity related to the electrons. But as we have increased the temperature at 300 Kelvin, which is our room temperature, then the electrons are moving. So this velocity is actually generated with the help of the thermal energy. So that is why this velocity is known as thermal velocity. The velocity which is actually related to the Brownian motion of the electron, that is its thermal velocity. Thermal velocity of first electron. U2 is the thermal velocity of the second electron, and the same way UN is the thermal velocity of the nth electron. That means the average, if we calculate the average thermal velocity, U is equal to U1 plus U2 plus dot UN divided by N. So one thing I was just telling, that if this thermal velocity is not equal to 0, that means this material is producing a current. Because if the electrons, the net thermal velocity of electron is not equal to 0, then there is a net displacement of the electron from one place to another place within the material, and that actually produces a current. Because how current produces? An electron is moving from one place to another place, and that produces a current. So as we know in our practical world, that if we don't use or apply any external electric field, then material doesn't produce any current. Then we know that this average thermal velocity, it should be 0. That means if we have n number of electrons within this material, that means at a particular time exactly n by 2 number of electron is moving exactly in the opposite direction of the other rest n by 2 number of electrons. If this n by 2 and this n by 2 electrons at a particular time is moving in exactly opposite direction within the material, then u1 will be equal to minus un minus 1, u2 will be equal to minus un minus 2, and so on. That means this u equal to u1 plus u2 dot plus minus of u2 plus minus of u1 divided by n, and all those will get cancelled with each other and will produce the result u equal to 0, which means the average thermal velocity is equal to 0. That means without applying any kind of electric field, it is not that electrons are in stationary state. No, they are not. They are moving. But half of the electron at a particular moment, if we consider at a particular moment, then we will see within that particular material that half of its electrons are moving in a way, and half of the electrons are exactly moving to the opposite of the directions which other half are moving. So if you are getting complications, then I am repeating it again. Suppose we have n number of electrons at a particular moment. If we see that n by 2 number of electrons are moving in right direction, then n by 2 number of electrons will move at the left direction, so that there is no net thermal velocity. If any electron is moving in this direction, there is at least one electron in the material which is actually exactly moving in the opposite direction of this electron. If one electron is moving in this direction, one electron will be there which is moving in this direction. If one electron is moving in this direction, another one electron will be moving exactly at the opposite of this direction. So that the net thermal velocity of the material will get 0. So I hope I am clear, and I have been able to make you understand the concept of the thermal velocity and the motion of the electrons without any external electric field. So right now I will discuss the motion of the electrons in the presence of any external electric field. That is our case 2. Under an electric field, external electric field. So if I consider about a material which is actually connected to a potential difference V, so of course the electrons which are negatively charged, they will be attracted by the positive side of the material. So all the electrons will move from right to left. But there is a problem, that it is not easy that I'm just connecting a potential difference across the material and all the electrons will move at a straight line, along a straight line. It is not like that. We are dealing with the material at its room temperature. So of course there will be a Brownian motion. It is not that when we will apply an external electric field, then the Brownian motion will be absent and only a linear motion will be there. This is not the case. There will be a Brownian motion, but when we are applying electric field, then the net displacement of the electron will not be 0. In case of in the first case, when we were dealing with the material when there is no electric field, then we told that the electron in the Brownian motion, the electron is moving randomly, and after some time it is returning returning back to its primary state, primary space, primary position. So the net displacement is equal to 0, and again this electron is following a random motion, and again it is coming to its primary state. So the net displacement of the electron is 0, but here the case is not like that. Electrons are following the Brownian motion, but it will get a pull. It will be forcefully pulled towards the positive terminal of the voltage source. That means if the electron is here, it will follow a Brownian motion and it will come to this place. So there will be some amount of displacement which is not equal to 0 right now. So this electron will not follow a linear motion. It will be following a haphazard motion, Brownian motion, but it will be having a linear displacement with its Brownian motion, and that linear displacement is caused by this external voltage source which we have connected with this material. So within the absence of the without the electric field, there is only Brownian motion. But when we are applying a electric field, external electric field, then the electrons are not only having its Brownian motion, it is having its Brownian motion, but as well as it will be having a linear displacement from its primary position, and that is caused by this external electric field which we have applied. So the velocity at which the free electrons are moving from right to left direction is known as drift velocity. So if I talk about the current, I is equal to V by R. R, we know that R is equal to rho L by A, where rho is the resistivity of material. So L by A. So from here we can write, and of course we know that resistivity is equal to 1 by conductivity, and conductivity of any material is equal to if we consider the charge carrier as electron, then conductivity that is equal to electron density into charge of electron into the mobility of the electron. So don't worry about the mobility term right now. We will discuss the mobility in very detailed manner in our later videos. But I just wanted to show you one thing here, that the resistivity is actually a function of the density, electron density. So to show you that the electronic density is the ultimate property of any material, I just wrote this resistivity formula in this way. I will talk about this mobility term later, but right now I just want to show you one thing, that this resistivity, which is actually a property of material, that is also a function of the electronic density. So what I told in my first video, that electronic density is the ultimate property of any material. So this is actually proven mathematically in this analysis. So I just wanted to show you that. So everything, almost all the physical properties of any material is actually a function of its electronic density. So I guess the motion of the electrons within a material is kind of clear to you right now. I have classified this whole discussion into two different subcases. One is without any external electric field, and another one is with, or you can say under an external electric field. So I guess up to this level, this is clear to you if you have followed my videos till now. And if you feel any doubt, then of course you can ask me in the comment section. I will definitely try to solve your problem. I will definitely try to solve the doubt you are facing. So thank you. This video is I think a bit longer than my previous ones. So okay, anyways, thank you very much, and take care. Bye bye.